Let's look at a popular distribution called weibull distribution. This is a way to model potential likelihoods. This is one way of modeling it, and weibull provides a generic enough function that can be adjusted based on two different parameters. One is shape and second is scale. So a general definition of weibull is it consists of two different parts. One is the cumulative function or saturating function. This basically is a function that that could be assumed of documenting the eventual progress. For example, progress was a given destination, and hence it is represented as unity, which is 1 minus e is to minus x scaled by a constant k3, and the scaled value is then raised to the power k4, which is the scale function. So we have a shape function and a scale function, and that's our saturating function. And then when we take the derivative of this function, then we arrive at the incremental distribution function. So we're not going to list the derivative of this function. That can be, anyone with basic understanding of calculus can do that. A quick way to model this in R is, just to use of two. Again, similarly, we have two different functions: R weibull and D weibull, right? So D weibull is the density, and R weibull is the random deviation, the random generation of values as per the shape and scale. And D weibull is it takes that random generated value as input parameter x and applies the same shape and scale which R weibull had used in generating the random values in the first place. And we're not going to use the log parameter here. We're just going to quickly plot x and w with respect to each other. And quickly see this is to to plot this and see how it moves from an exponential distribution to start with for lower values to a bell curve, a shifted bell curve. So this is how it looks. Let me run this again. And you can see that it moves from an exponential value towards the start towards a shifted bell curve, and then when I change the values of shape and scale respectively in cascade follow.